So this is the last in the series of the 3 lectures, and this is going to be the most fun one, hopefully, largely because I hope to be able to play a game with you and then unpack that game and the way that you solve the problem using the principles that we've been rehearsing in the first 2 lectures. So a lot of this lecture just reproduces the previous lecture. But the purpose is to apply the same ideas at a number of different levels to get an insight into insight, or more specifically, discuss active inference and self-evidencing from the point of view of why we are curious creatures and how different levels of optimization can be understood in terms of a free energy minimizing process. So the idea here is that we're going to be talking about different levels of recognition and inference, making a distinction between inferring states of affairs in the world, hidden states or latent states that are generating observations, learning the parameters of a model, and then crucially learning about the model itself, namely learning the structure of a model. And within that, in terms of planning as inference, understanding the different kinds of intrinsic value or intrinsic motivation, I'm going to make a particular distinction between resolving uncertainty about states, which is part of that expected free energy functional, in terms of responding to salient cues in the environment, and resolving uncertainty about the parameters of generative models that I'm going to associate with the notion of novelty. What would happen if I did that? So to summarize, we're just going to rehearse what we've already done, but broaden the scope to include not just inferring what's going on in the moment and planning the policies that will solicit the right kind of data to optimize that inference, but also consider the optimization of the model in and of itself. So inferring states of the world, learning model parameters, and crucially learning the model structure, known as structure learning in cognitive Bayesian science. In statistics, this is just Bayesian model selection, selecting the model that has the greatest evidence or renders the data the most likely, in the sense of having the largest marginal likelihood or the greatest model evidence. To illustrate how these different levels of optimization interrelate, I want to play a game. I'm going to ask you to play that game with me, and then we're going to try and record how quickly you can solve a problem. It's going to be an abstract rule solving problem. Then ask, can we simulate that kind of problem solving, and can a Bayes optimal agent simulated either be more optimal than you or less optimal than you, and if it's less optimal, why is it less optimal? So this will require a bit of interaction with the audience. So I'm wondering if somebody can volunteer to switch the microphone back on again, because what I'm going to do is ask you to tell me when you think you've discovered a rule, and I'm going to be particularly interested in how many bits of evidence, how many data points you need before someone can recognize or find the correct rule. So here's the game, or the challenge. You're going to see a series of panels that contain 3 colored squares, and what I want you to do is tell me the correct color based upon the arrangement of these 3 circles. So for example, if the correct color is blue, you would say blue. And there is a rule that enables you to identify uniquely the correct color. What I will tell you is that the location of the correct color depends upon the color of the upper circle. So the rule, the location, it could be, say, red, depends upon the color of the central square here. So that's all you know. Those are your prior beliefs. And now, if blue was the correct one, I'm going to sorry, if the color blue designates, say, green as the correct one, the circle or the stimulus on the right-hand side, then I'm going to record the correct one for you and then keep a record of that, so you don't have to keep it in working memory, but you can just look at the previous data points and try and work out what the rule is. So let's just start. We're going to play this game several times, and I repeat, I'm going to be interested in at what point can somebody recognize the rule. So let's just start. Do we have a volunteer? Can anybody come up to the front with the microphone? Is that possible?
Today, I will mimic for a reinforcement learning agent.
Thank you very much. Right, so your job is to, if anybody puts their hand up when they think they have the answer, I'll ask you to ask them what they think the rule is. But I'm going to ask you first of all. Let's just start with this, the first trial of this game up here. Which do you think is the correct color?
I would pick green.
You're going to pick green. And yeah, you're absolutely right. That's remarkable. And of course, there is no way that you could have guessed the rule on the basis of the first data point, but you are absolutely right. Well done. Have another go.
Blue one.
You're going for blue. Ah, well, that's an interesting choice because there is no blue circle there. So we know it can't be blue. It has to be either red or green.
Oh.
Have another choice.
So, actually, now my choice would be just two variants. So I have two guesses which will, with 100% probability, lead me with the correct answer. Okay, yes. So I choose red.
You're going to go for red, right? I'm afraid it was green. I'm very sorry. Have another go. Have a third go. Well, in principle, this is a very easy one. I should say that these colors were chosen at random. Well, perhaps you will now know why this is easy. What color which is the correct color?
Well, my Bayesian inference framework inside my brain said that it's red.
Yes, because it can't be anything else. So that's not a very informative one. Because it's not very informative, have one more go. See if you can guess the correct color out of the green and the blue here.
So let's choose green.
Well done. Do you or does any member of the audience have any idea what the rule is at the moment?
Yeah. The audience is hinting me that the rule is the following. So if we have just some green color among the three above, then the correct answer is green. Otherwise, what's otherwise? Well, otherwise, the upper one. So this seems arbitrary to me because we have no information about not enough information about this case.
Yeah, you made some very good points here, and I'm doing this very slowly for a particular reason. So don't feel rushed. Let's just discuss how what rules might be in play, and you'll see why I'm taking this very slowly later on. And it's also, I think, very interesting that some of the rules that come up earlier are going to be plausible but false, so they're going to be specious rules, and that itself is extremely interesting as well. And also, you're absolutely right, there's not enough information at the moment for you to definitively say, this is the rule. Either you or anybody who thinks they know, they have an idea about the rule, can you apply the best rule that you have to the next one, to the next game here?
Okay, so I'll give it a try. I think that the correct answer in the next picture is green.
Very clever. Do you want to try your hypothesis for the next one?
Surely. Okay, so let's make a voting.
You're going to vote, excellent.
Green.
Well done. Okay, I'm wondering if you or somebody else has actually discovered the rule. Do you want to ask the person, somebody's got their hand up behind you. Ask the person behind you whether, and tell me what you think the rule is.
So we are now concluding the rule, just 1 second. So there is a hypothesis that the correct choice depends not only on what is exhibited on the present picture, but also on the previous one. So this is actually, it seems like a nice idea for me. So we choose green if there was green color on the previous picture. But actually this hypothesis is crushing on the third picture, so the first row on the right. There are hard debates where, sorry.
This is very good. There's no rush, take your time.
Okay, so we want to continue playing because it seems like the next example will give us more information about what happens when there is no green.
Okay. Color. What would you like for this one?
What would you like for this one? We are voting for blue.
It was red.
The chat does not agree to us, but we are choosing blue. The correct answer is red?
The correct answer is red. So remember your priors. The location just depends upon the color of the central circle. So I've never heard the idea it depends upon the previous one. That's very clever as a hypothesis, but that's an example of one of these specious hypotheses. But that is not correct, although very clever. That you should be able to discern the rule simply based upon the color blue or red or green of the central
Then I have a stupid question. Then, why do we need three colorful circles if the location of the proper color depends on the upper one? Or do I misunderstand something?
Could you repeat that? Sorry.
So the location of the correct color depends upon the color of the upper circle, right?
Yep.
Why are we offered the task with three circles? So what should we conclude from the other two?
Right. So the correct color is encoded by the color of this circle. So it could be this circle, or it could be that circle, or that circle. Remember that these three at the bottom are just to allow you to remember which was the correct color. So the color blue tells you whether it's either red, green, or blue. The color red tells you which of these circles has the correct color. The color red here, similarly, the color green here, because it's green, it tells you whether it's on the right or the left or in the center.
Yes, so this is the answer. Actually, I was trying to figure out what should we guess in this setting. Okay, so this is a very nice game, actually.
So do you think you have the solution?
Okay. So the audience had an interesting hypothesis. If the central color is red, then we're choosing then we're choosing the left one. Yeah, this one. If the central color is blue, then we're choosing the right one. And if it is green, we're choosing the central one.
That's perfect. That's very impressive. Well done. And I mean well done very sincerely, because even with audiences that comprise 500 people at places like MIT in the United States, they still take about 5 to 6 to 7 moves. So for such a small audience like you to discover that basically in 1, 2, 3, 4, 5, 6, 7 in 7 moves or bits of data.
I think we should add this to our CV, because
Absolutely. But it is remarkable. And it's also remarkable because, as we'll see later, just on the principles of Bayes optimality, what you have just done is impossible. It's mathematically impossible for you to get the correct rule with so few data points. So that's basically what we're going to try and understand in the remainder of this talk. So just to reinforce your correct identification of the rule, red to the left, green to the center, red to the left, green to the center, green to the center, red to the left, blue to the right, and red to the left. Oh, sorry, no, red. Yes, red to the right, which is blue. Good. Right, so well done. Thank you very much. That's the first time I've ever done this game using Zoom, which is very encouraging. Okay, so now what we're going to talk about is very briefly rehearse the slides which we had in the previous presentation, and then put the products of that kind of inference into to work to try and understand how you solve that problem. So you've seen these slides before. I'll just very briefly go through them so that we are reminded of the formal structure of this calculus, this belief updating. We are going to motivate a expected free energy functional on the basis of optimizing not a function of states, but beliefs about states, probability, Bayesian beliefs or probability distributions over states conditioned upon a sequence of actions leading to a variational principle of least action that decomposes sentient behavior into inference based upon the best explanation, the posterior or approximating posterior over states of the world under a policy, and then use that to evaluate, roll out into the future, the consequences of a plan in terms of the intrinsic and extrinsic value as summarized by the expected free energy. And we've already talked about different perspectives and different parts of these, how they relate to things like Bayesian surprise, epistemic affordances, KARL control, risk-sensitive control, and standard expected utility theory that discount various sources of uncertainty and to produce various special cases. And the story basically is that we can summarize in the most general way the goodness of a policy in terms of expected free energy that is just a mixture of the information gain and the expected utility or the expected model evidence. And we can decompose that into expected value, where we're not changing our uncertainty about the beliefs, plus a bit which is much more about foraging for data and then shrinking our uncertainty to have a more precise posterior. And then when we put them together, we get this mixture of explorative and exploitative behavior that combines the notions of Bayes optimal decision making and optimal Bayesian experimental design. This is just a recapitulation of the generative model that we're going to use. We're going to use this Markov decision process model to actually model that game that we have just played, and then make a synthetic agent play that game and see how quickly that agent is able to infer the rule and then respond confidently with the correct color at every exposure. So just to remind you, we're talking about a Markov decision process. That's just shorthand for a generative model of discrete states that generate discrete outcomes via a likelihood mapping, where the transitions among states depend upon priors encode or depend upon probability transition matrices, usually denoted by B, that depend upon the policy, and the policy depends upon our expected free energy that is defined by our log preferences, sometimes encoded in a cost matrix C that has some additional parameters modeling the precision of our beliefs about what we are going to do, the initial states, and some hyperparameters should we need them. And then given a functional form for the approximate posterior, we can then use conventional variational message passing or belief update equations to write down a simple belief updating scheme that not only covers unknowns such as expected states of the world, but also the plans or the policies that we are pursuing and the confidence or the precision we place in those plans or policies, learning about the unknown parameters. Remember, D was the context, and action selection. And we've already gone through this example. Just to remind you, we're trying to understand the relative role of the the Bayesian optimality in terms of designing experiments in the sense of our perception, our active perception, our active vision, our active sensing being thought of as an experiment that is designed to test, in the words of Helmholtz, hypotheses about what might be generating our sensory impressions. And then on the other side, the expected evidence itself becomes a pragmatic or expected utility or preferred or attractive state. So once we've resolved our uncertainty in an environment that we can become familiar with, there is no more salient or epistemic affordance, and we can then indulge in this exploitative behavior. What I want to do now, though, is sort of take that basic idea and unpack it in the context of that game, just to highlight a number of different levels at which these quantities, these contributions to the expected free energy and the variational free energy emerge and define different kinds of learning and inference and selection in the sense of Bayesian model selection. So here was your game again with your 3 circles and the correct outcomes encoded along the bottom. Now, if I now want to create an in silico agent that can also do the game, play the game that you have just played, I have to be a little bit more precise in terms of what it has to do. So for you, it was easy for you to saccade around, look to the different circles and tell me using the microphone what your choice was. I have to write that down explicitly when creating a generative model of this game. So I have to write down various policies in terms of sequences of eye movements that target the different circles and write down what I would see if I was looking at this circle or that circle. Basically, a generative model that can solve the problem of where to look next, and when confident about the next correct, the correct color, then use eye movements to indicate at the bottom what the correct color was. So to specify such a model, I have to specify the outcomes that this agent is going to sense and all the necessary hidden states that I can use to generate those outcomes. So it's relatively simple. In terms of what I'm looking at, it can have 3 different colors, or it can be a null color, the starting position. So this is the color that I see. I also know where my eyes are pointing, so I can be in the center, start the left or the right. And I also know what I've chosen in terms of giving the experimenter feedback. Either I'm saying I don't know, or sorry, the experimenter giving me feedback. Either there is no feedback at the moment, or the experimenter is saying, yes, that was right, or no, that is wrong. So you can regard this as some auditory outcome, which is positive or negative or null. But in order to generate these stimuli under this structured, rule-based world, I have to now write down all the hidden factors and states that could possibly generate in a lawful way these kinds of outcomes. So what do I need to know? Well, I need to know what the rule is. I need to know whether it's the correct color is a central color, or whether it's the color of the circle on the left-hand side or on the right-hand side. I need to know what the color of the circle is. I need to know where I'm currently looking, and I need to know what I have chosen in order to generate some feedback. And with all of these things, if I knew what the rule was, and I knew the color of the circle at the correct location, and I knew where I was looking, and I knew what my choice state was, I can generate all of these outcomes. So what I need to do is to be able to write the mapping from these causes or hidden or latent states and their observable consequences, and that will be my generative model. So this is all about that likelihood mapping from states to outcomes encoded in an A tensor. And I've tried to unpack that A tensor by tiling out the various slices, the likelihood mappings under different contexts. So this is what is actually generating the outcome. So this is a description of the rule as written down in a probabilistic mapping from causes to consequences. So this is the generative model. So for example, if there is a red in the center location, or if I was looking at the center location and I saw red there, then there's only a lawful relationship between the correct color and the color at that location on the left-hand side. If I look at the wrong side, there's no relationship between the color of the circle at that location and the correct color. So the rule really is this context-sensitive, precise, unambiguous mapping between cause and consequence that exists only in a particular context and not elsewhere. And that context is identified by a Q, which is just the color of the center circle. But of course, you don't know that, and my agent doesn't know that. So from her point of view, there is no structure here. So we start off before experiencing any outcomes with a prior mapping. We do know that there we do have the prior belief that the color of the center has some importance and designates the context, because that's part of your prior beliefs. I've told you that the rule depends upon the color of the central circle, but what that rule is, we don't know. This is the true rule. This is the beliefs that we start with. But in principle, by accumulating evidence, given the contingencies, the generative model, the likelihood mapping that map from causes to consequences, it is possible to learn the structure of this likelihood model, the structure of this generative model, or the parameters of this generative model that now come to embody the rule. The question is, how quickly and how many data points do I need to do that? So if I now just take those equations, those standard belief update or variational message passing questions under the generative model of the previous slide, and see how quickly the agent is able to infer the correct color, I can get an idea of how many data points or how many experiences this agent needs before she learns how to identify the correct color. So as before, as with the two-step maze graphic, I'm denoting the correct color or the initial state with these colors here and the various policies. And the policies here are just, do I look to the left and then the center, then the right, and then make a choice, or do I move to the right and then the left and then make a choice, or do I keep on sampling and looking around? And this is the performance here scored in terms of the free energy and the associated confidence in the choice that has been made. And what I should say that the mistakes that the agent makes by basically declaring or choosing the wrong color are in red, and the correct choices are in black. So we see for the first 14 moves, there's a mixture of rights and wrongs here. But after the 14th exposure, the 14th trial, this agent is able to learn enough to perform with 100% correctness or accuracy, at which point she becomes quite confident about her policies and her choices and her responses, and then the physics free energy consequently falls. So this is the negative elbow in machine learning that reflects or is reflecting partially this increase in confidence. So what we have here is a mathematical model of rule learning just by learning the parameters of a likelihood mapping in this sort of multifactorial generative model. And it's interesting because we can go in and start to ask, well, what differentiates the belief updating and the physiological correlates of that updating that we might see if we were actually looking at a human being or a mouse doing this task, before and after learning the rule. And we can do that quite nicely because there are certain stimuli that have been identically sampled with a sequence of eye movements before and after this simulated agent is able to respond with 100% accuracy. And then we can just compare the responses and the belief updating between these two trials. Before I show you the results of that, I want to ask a question and then answer it. You may be asking yourself, well, why are we looking anywhere? In the sense that the consequences of action in this instance have no meaning from the point of view of a reinforcement. There were no preferences here. Everything is now being driven purely by this intrinsic motivation, the desire to resolve uncertainty. But there is no uncertainty to resolve in terms of hidden states because you can see the colors of everything and you can hear exactly what's going on. So there's no ambiguity in play in terms of the states of the world, the stimuli generating this agent's sensory input. However, there is another kind of uncertainty that can be resolved, and clearly that's the uncertainty about this likelihood mapping. It's about the parameters of the generative model, not the states generating outcomes under the parameterized generative model. And I've cartooned that here just by creating a slightly extended version of this computational architecture to highlight the fact that there's not just states that we have to infer. We also have beliefs about laws and contingencies that are entailed or encoded in things like the likelihood mapping and in other contexts, the probability transition matrices. And these things are themselves subject to exactly the same analysis that we had before. So in terms of expected free energy minimization, the intrinsic value now becomes novelty. So as previously, we can update our beliefs about states by simply finding a posterior over states that minimizes complexity but maximizes accuracy by minimizing or optimizing the free energy. Exactly the same thing is being done with respect to parametric learning or learning the parameters, finding those values of the likelihood mapping, that matrix that optimize a free energy functional of the observations. But we can also follow through our uncertainty about the parameters into the expected free energy. And basically what happens is that the intrinsic value or the information gain about the parameters, namely the KARL divergence between the posterior, conditioned upon observations in the future, given a particular policy, relative to our beliefs before seeing those observations and inferring the states that generated those observations, scores the information game. So the expected free energy, the contribution to the expected free energy due to uncertainty about parameters now becomes novelty. So there is a novelty here just by looking around and seeing what would happen if I did that. Now can be quantified in terms of the intrinsic value due to information gained about the likelihood mapping or the parameters of my generative model. And that's going to get into the beliefs or the expected free energy and my beliefs about what I should do next. So I'm just saying that again, but unpacking it for you by expressing the expected free energy in terms of our utility and the intrinsic value related to beliefs about states. That is the information gain we have in relation to posteriors over states. And crucially now, exactly the same functional form emerges when we incorporate or include posterior beliefs about the likelihood. In the brain, these are going to be encoded by connection strengths. In a machine learning or neural network, these would be the connection weights that we're talking about. But here they play a very particular role because we have a generative model. They are likelihood mappings. So basically what we're talking about is an epistemic affordance that scores a novelty. What would happen if I did that? And that child is about to find out. So what I want to do now is remember that it took about 14 moves or 14 exposures before this synthetic agent was able to respond correctly and confidently. And that's what I meant when I was congratulating you in doing this after 6 exposures, because this agent is Bayes optimal. You can't get any better behavior than this agent. And yet you were able to do it. In fact, you were able to do it after 6 moves, but most people take about 7 or 8 exposures before they get the rule. So that, in principle, is mathematically impossible. So the question now is, how did you manage to do it? So does anybody know? I'll ask the audience again. I'm not necessarily anticipating an answer, but if somebody in the audience has an answer, what's different between what you were able to do or the prior beliefs that you had and the prior beliefs that I equipped this agent with that could possibly explain why you are better than Bayes optimal? Does anybody have an answer? If you do, perhaps you could use the microphone and...
Работает. Hello, my name is Gosha Noikov. Well, I think that the prior knowledge of the agent that you presented to us was wrong, because the actual prior knowledge of us was the distribution on the matrix A. And you, as far as I understand, have only like one matrix A. And then after each new card, you showed us with the correct answer, we updated not the matrix, but the distribution of the matrices. So after each presented correct answer, a lot of matrices receive 0 probability mass, and then they just go out from the equation. So after the, at the end, there was only, after 6 trials, there was only one matrix with non-zero probability.
Very good. Yeah, that was a very technical and excellent answer, which you know, I think captures exactly what I was hoping you would say. If I just reword your description slightly more heuristically, so you make the very sensible observation that you were able to exclude various hypotheses that were impossible, or given certain outcomes, and therefore much more efficiently be able to identify the remaining hypothesis or rule in a way that this agent was not able to do. And I think that's absolutely right. So what one way of putting that is that although this agent still had all the information and was still able to remember and accumulate information about the past and the present, what she didn't have was a hyperprior that there was a rule. Whereas you knew there is a rule, and therefore there are certain rules that you could entertain. And if a particular rule or hypothesis was excluded by any of the evidence in the past, you could take it off the table and eliminate it. Whereas this agent couldn't do that. So that is, I think, exactly why you were able to outperform the space optimal agent, simply because you have in your head the notion that there is a small number of discrete rules that could explain this. And I think what you were doing when you were conversing before you actually discovered the correct rule was going through a series of hypotheses and seeing if it was a good explanation for the data, and if it wasn't, excluding it because they had zero probability mass, and then moving on to the next one. So you were able to actually go through a number of limited hypotheses and explore a model space. And in the jargon of Bayesian model selection, that would be selecting the right model from a number of competing models or competing hypotheses. This is, if you like, an instance of structure learning, where we will associate the structure with a particular model or a particular constraint on the form of the likelihood mapping, which you nicely describe in terms of setting certain values to zero or not setting them to zero. So from the point of view of the free energy functionals, what we are now talking about really is something priors of the kind that pertain to the contingencies and rules that govern the way that the world works and generates data for us. But we're also now trying to optimize our prior beliefs about the form of those structured mappings as parameterized by the likelihood matrix here. So previously, we've been worrying, or we have been optimizing the free energy functionals with respect to beliefs, posterior beliefs about A. But we can also think about how would you optimize the prior over A in order to minimize the variational free energy, or optimize the variational free energy. And one way of doing that is by trying out different A's where their structure and form is encoded in their sparsity structure, with different combinations of certain elements being set to zero so they have zero probability mass. And when we consider, well, let's just look at a hypothesis, space. This is the posterior after learning of that A tensor, separating out slices of, if you like, a collection of likelihood matrices mapping from causes to consequences. This is what was accumulated just by experience. And these are different priors that we could have used. A prior which is a completely agnostic prior, where there is no rule, but it might have been this rule. It might have been that the center, certain colors suggested that the right-hand circle was contained the color of was colored with the correct color, as opposed to the left-hand one, which is the correct rule. And you can imagine all sorts of different structures and sparsity structures here that are all characterized in a regular way by certain elements being set to 0. So that's really a definition of a rule. So what you knew that the agent didn't know is that the true likelihood mapping had to be selected amongst a number of rule-like priors or structures. And when we include that, if you like, hyperprior into the optimization scheme, we should be able to recover the kind of behavior that you saw. Before we do that, though, I just wanted to bring this notion of structure learning and carving in a way not dissimilar to what we're talking about previously in relation to deep learning networks, where you want to simplify and remove redundant parameters and redundant weights and redundant connections. In the same way that this is the kind of model reduction or simplification you get from Bayesian models selection or structure learning. So the idea here is that you start off with some over-parameterized network or mapping from the point of view of a generative model. Could be a probability transition matrix or a likelihood mapping linking one level to another level of the sort we saw in the previous presentation with deep generative models. It doesn't really matter from the point of view of this graphic. The idea is that we have an over-complete model. We then expose it to some data, and these connections remember the associations using the free energy optimizing belief updates, which are simply basically co-occurrences or associated plasticity. So for the likelihood mapping, the conjunction or co-occurrence or the outer product of the posterior over the causes, the inferred causes and the consequences. This is added to Dirichlet parameters and accumulated so that when we renormalize it, we now have a more precise and confident belief about that particular conjunction or likelihood or co-occurrence of causes and consequences. And we accumulate more and more strong connection strengths, if you like. We accumulate associations in our over-parameterized model. And then the structure learning goes through and says, well, look, what would happen if I set the probability mass over this particular association to 0? Would I get a simpler explanation and therefore increase my model evidence or optimize my free energy? So the change in free energy is actually a very, very simple function based upon beta functions here of the difference with and without setting that particular Dirichlet parameter, that underlying connection strength, if you like, to 0. And sometimes the evidence will go up, which means that you've actually removed a redundant parameter that was contributing only to the complexity. And sometimes the evidence or the change in free energy will be in the other direction, which means that you've now compromised your ability to provide an accurate explanation. So you can go through all the connections and prune them by removing redundant connections according to this very simple rule here. If the change in free energy is of the sort suggesting that the connection, the parameter, your posterior expectation of the parameter was just added to the complexity, then you can remove it and you can retain it if not. So in the brain, that's known as synaptic regression. And many people think that that's the purpose of sleep. So, and indeed, your original formulations of a restricted Boltzmann machine and the sleep-wake algorithm in a sense, use this kind of optimization at the level of the structure or the reduction of the structure or the form of the model itself. So the idea is that we spend our day learning associations, plausible laws in our experienced and lived world. And then when we dream at night, we rehearse those associations, those scenarios, but in the absence of any sensory data, so we can concentrate on the complexity and evaluate the complexity. And if the complexity goes down by removing or regressing a synapse, then we lose it, but we will, if it doesn't, and usually with larger synapses, we will keep that synapse, so that we've now got a much simpler, more parsimonious, less overfitted model of yesterday's experience that then we can take into tomorrow's exposure. And of course, it doesn't actually have to be during sleep. We can do this whenever we think about something. So if we ignore, we close our eyes, or we meditate, perhaps not meditate, but certainly if we just stop acquiring data for a moment, we can still optimize our generative model in the sense of minimizing its free energy by minimizing its complexity, because we do not have to worry about the accuracy term, because there's no data to explain. It's just the data that we've seen so far. So when we equip the model, that little agent, with 36 hypotheses that were just defined by having regular patterns in this likelihood mapping, where the pattern was defined by what connections had to be zero, basically sparsity patterns. This is what we see. We didn't actually put the agent to sleep. We let the agent think about things, have a little nap between experiences, and then do its pruning, or to do her synaptic regression or Bayesian model selection. Technically, this is Bayesian model reduction, because we're reducing an over-complete model in between different experiences. So here we have the true rule as encoded by the likelihood mapping. Here are the priors, and here after the 12th observation are the posteriors without and with this sleep, this Bayesian model, sleep-like Bayesian model selection under the hyperprior that the model itself has the likelihood mapping has a sparsity structure that is like a rule. And you can see immediately that the benefits are with exactly the same information. The posterior now looks a lot more like the true contingencies as encoded again in this likelihood mapping. So this becomes now a process which is beyond just learning and accumulating experience in the parameters of our generative models. There's actually a categorical act of selecting this model over that model, in the sense of removing a particular component, connection strength, layer, whatever you want to consider. So there's a discrete jump, a saltatory jump from one belief to another belief as we switch and select a new model. And in that sense, we can interpret this as the acquisition of insight in the moment. So in the psychology literature, this would be an aha moment, a revelation. Oh, it's as simple as that. This is how it works, which I'm hoping many of you experienced when you suddenly realized what the actual rule was. This wasn't a gradual learning and becoming more and more confident and competent in understanding the contingency or the rule. You either understood it or you didn't. You had lots of hypotheses and lots of uncertainty, but suddenly there was a resolution when you found the one that fitted. And the proposal here is that this process of structure learning is the homologue of that kind of insight that we experience psychologically. So when we look at the performance of agents with and without sleeping or model reduction, we see the kind of performance that now is approaching your competence. So here is a sequence of agents. There were 64 agents run with and without having a little sleep in between the trials to do the structure learning, showing on average an improvement in performance and a decrease in the average free energy and an increase in blue here of the confidence. But most interestingly, of course, is at what point did they have their insight? When did they discover the rule? And indeed, what we see is that some of these agents now became as good as you and were able to discover the rule after 6 exposures. So the first agent here, in fact, was exposed to exactly the same stimuli that you were exposed to when we played the game. Interestingly, this particular agent settled on or selected the wrong rule, which was a little bit like, which is why I was asking you to try and remember all your false hypotheses that you couldn't completely confirm or reject on the basis of the evidence at hand. This synthetic agent is also subject to that constraint. So once you commit to a particular model, it may not necessarily be the right model. Of course, once you've committed to it, then you're not going to be able to recover unless you go back and do some more structural learning after you've acquired more evidence. So this, in the psychology literature, would lead to superstitious behavior under a plausible but false belief about how the world works. Fortunately, you were able to have both your superstitious and correct beliefs be manifest, and indeed more quickly than even this now truly optimal Bayesian agent was able to show. So in summary, we've spoken about sources of uncertainty and understanding self-evidencing as putting constraints on the kinds of behaviors that I commit to, and the imperative being to minimize expected free energy, expected prediction error, expected evidence that usually can be cast in terms of reducing a source of uncertainty. And what are the sources of uncertainty? Well, they could be about states of the world, and the resolution of that uncertainty concerns planning, and we can think of that in terms of inference, active vision, responding to the intrinsic value or epistemic affordance that psychologically we might construe as salience. But there can also be uncertainty about the parameters of a model that we can resolve by learning, and this is largely the focus of machine learning that considers usually the weights of neural networks. And when we consider the uncertainty reducing aspect in terms of the intrinsic value, and then psychologically or in the psychology literature, that might be best described more as novelty. But we also have uncertainty about the hypotheses, the generative models themselves. As scientists, we entertain multiple hypotheses, discrete hypotheses, explanations for the data that we solicit, and then we solicit the right kind of data by the right kind of experimental design, and then change our mind literally to adopt a different hypothesis and a different structured or formal understanding that embodies knowledge via this process of Bayesian model reduction or selection. So that may or may not involve going to sleep, but it certainly does involve coming back to this notion of minimizing complexity as one important way to resolve uncertainty or optimize the expected free energy. So again, everything should be made as simple as possible, but not simpler. And again, I just want to thank those people whose ideas I've been referring to. And for the last time, thank you for your attention. Thank you very much indeed.